Okay, today we're going to talk about the Schrödinger equation, the time-independent Schrödinger equation in 3 dimensions. And in particular, we will be talking about the hydrogen atom. So far, our discussion was limited to 1 dimension, basically. We had 2 examples that we talked about. The particle in a box and the simple harmonic oscillator, and both of them the position of the particle was just represented by x, so the underlying assumption was that this particle is confined to just live on the x-axis. And when we talked about, let's say, probability and the interpretation of the wave function, so for 1 dimension, we set psi of x, and it can be time dependent, so it can be a time dependent probability. Dx is probability of measuring the particle position in a range, let's say, x and x plus dx. So the underlying assumption is that the particle is confined on the x-axis. It can't be found anywhere on this axis, and we're talking about the probability of finding it, somewhere in a tiny interval of length dx at position x. Now, when you talk about higher dimensions, again, we have to talk about the probability of finding the particles somewhere in 3-dimensional space. So if you want to think about like an infinitesimal volume element in 3D, we can have something, we can think of a cube, right? So there's going to be, we can imagine a cube of length, let's say dx, dy, dz. So it has a volume, let's say dv volume is dx times dy times dz. And then it makes sense to talk about a wave function as a function of these 3 coordinates, such that psi of x, y, z, and t squared times this volume element dx, dy, dz is probability of measuring the position in that cube. So that means, for example, that x is between, the x component of the position is between x plus dx, the y component is between y and y plus dy, and the z component is between z plus dz. So by measuring the position of a particle that lives in 3 dimensions, you measure a vector, you find all the coordinates, basically. So this is kind of a generalized notion of volume, and you can play the same game in 2 dimension if you have a system. Let's say you have like an electron gas that's somehow confined to live in a or on a 2-dimensional surface of some material. You can talk about 2-dimensional analogs of this. Okay, so let's start by an example. So the material we're talking about, we just started chapter 7 of the book. So this is kind of, so here this is section 7.1 of Harris, talks about probability density in higher dimensions and wave functions in 3 dimensions in particular. And then section 7.2 gives an example about like a 3-dimensional infinite web. All right, so let's think about the Schrödinger equation. What would it look like? So in general, the structure of the Schrödinger equation is we have an operator corresponding to the energy of the particle times the wave function is some energy eigenvalue times the wave function, right? This is the time independent Schrödinger. So in 1D, H, what was it? It was the kinetic energy plus the potential energy, and the operator associated with the kinetic energy was minus h bar squared over 2m. Second derivative with respect to x, to position, so that was the operator corresponding to the kinetic energy, plus the potential that just depends on position. So if I want to generalize this to 3 dimensions, well, you can think about the kinetic energy is basically like k is p squared over 2m, right? And if you live in 1 dimension, that's just px squared is equal to p squared. Sorry, let's say p squared is just equal to px squared because there is 0 momentum in other directions. But in 3 dimensions, well, the total momentum, right, if momentum has components in the directions x, y, and z, let's call those components px, py, pz, this is going to be px squared plus py squared plus pz squared. Right, so that's the length of our momentum vector with those components, and you use kind of the Pythagoras theorem repeatedly, so that's the relationship. And in the same way that we identified the momentum in the x direction with, let's say, minus ih bar derivative with respect to x, we can identify the momentum in other directions analogously. So py, the momentum operator in the y direction, just has the derivative with respect to y, and similarly for the momentum in the z direction. So this, if I insert it into that, right, make these operators, we find that the Hamiltonian operator in general for a 3-dimensional system is going to be minus h bar squared over 2m, second derivative with respect to x, plus second derivative with respect to y, plus second derivative with respect to z. And then you have some, so that's the kinetic energy operator, plus a potential energy that can depend on x, y, and z. It just depends on position. So now if I want to write the general Schrödinger equation in 3 dimensions, well, it's going to be easy. It has the same structure. So I will write the same thing, except I use this 3-dimensional kinetic energy operator. So we find minus h bar squared over 2m, second derivative with respect to x, plus second derivative with respect to y, plus second derivative with respect to z, plus v of x, y, and z. This whole operator acting on psi x, y, and z should give me some energy eigenvalue times psi x, y, and z. All right. So that's the general Schrödinger equation. Basically, the only thing we did is kind of generalize the kinetic energy to cases where you can have momentum both in x direction, in y direction, and in the z direction. All right, so let's look at one example. section 7.2 of Harris talks about 3D infinite potential. Or particle in a three-dimensional box. This is actually more of a box than the line that previously we called a box in one dimension. But basically the potential is going to be, so V of, let's say, R, where R has X, Y, and Z components, is going to be 0 if X is between 0 and L, so 0 and L, and Y is between 0 and L, and also Z is between 0 and L. Okay, and it's infinity otherwise. So it's a direct generalization of the particle in a box, of one-dimensional particle in a box that we talked about to 3 dimensions. So if you think about the potential, you have a cube of side L, and there is zero potential inside the cube, so the particle can live inside this cube, and the potential outside this cube is infinite, so there's no wave function outside. You can't leak out. Again, it leads to divergences in the Schrödinger equation, right? So how do we solve this? Well, the trick is to use something called separation of variables. In the same way that when we were trying to find stationary solutions to the time-dependent Schrödinger equation, we wrote psi of x and t as some function of x, psi x, times another function of time, let's say phi t, and we inserted that into this general differential equation and tried to solve it. We can use the same trick here for this particle in a three-dimensional box. One can play the same trick for, let's say, a three-dimensional harmonic oscillator. All right, so let's do this. So I can write. So we use separation of variables, and we look for a solution psi of x, y, and z equal to f of x, some function of x, g of y, h of z. These are some functions we need to find. So we have this particular form. All right? Now, if I insert that into the Schrödinger equation inside the box, so outside the box, we have psi of x, y, and z is 0. Which again, because we want the wave function to be continuous, it means that the wave function is 0 on all surfaces of the box, right? So if you have, for example, x equals 0 and x equal L, psi should vanish. Similarly, if y is 0 or y is L, or z is 0 or z is L, the wave function should vanish. So inside the box, where the potential is 0, what can we write? Well, this V is 0 inside the box, so we just have this operator acting on that product. So let's do that. Is some energy. Okay. So see, this derivative only x on x, so it sees gy and hz as just constant, so it's going to be like just a second derivative of f, right, with respect to x. So on this side I'm going to get minus h bar squared over 2m gy hz, second derivative with respect to x of fx, plus, now this term has derivatives with respect to y, so only x on g term, so I have fx hz, second derivative with respect to y of gy, and then I have the last term, I have fx gy, second derivative with respect to z of hz. So this thing must be e f of x, gy, and hc. All right. So again, kind of the trick is very similar to what we did in deriving the time-independent Schrödinger equation. We just divide both sides by fgh. So what do we get? What I get is minus h bar minus, sorry about that, I don't know what's happening, minus h bar squared over 2m. Make it a little bit bigger. I think that's the issue. Yeah, so we find minus h bar squared over 2m. Then when I divide this by fgh, g and h go away, and I find second derivative with respect to x of f of x divided by f of x, plus, now you divide this by fgh, again f and h go away, so we find second derivative with respect to y of gy divided by y by gy, plus second derivative with respect to z of h over h. This thing is going to be just the energy. Right? So again, it's the same trick, right? We have something that's only a function of x, plus something that's only a function of y, plus something that's only a function of z, and they add up to a constant that doesn't depend on x, y, or z. Right? There's no way you can, if there is any dependence on x here, there's no way you can cancel it out by these terms that don't depend on x. So the only way that's possible is that this function of x is a constant, this function of y is a constant that doesn't depend on x, y, or z, and similarly this function of z is a constant that doesn't depend on x, y, or z, and that's the only way we can satisfy this equation. So the only way we can satisfy this, which is a sum of a function of x, a function of y, and a function of z being equal to constant, is that each term itself is a constant. So I can call those constants ex, ey, and ez. And then, of course, Ex plus Ey plus Ez is my total energy. But then we're basically done, because, oops, there's a minus sign here. Sorry, the minus sign was already there, so let's get rid of that. Okay. So notice that each of these, right, is just a one-dimensional particle in a box. So we're basically done, right? So when we had just one 1D particle in a box, the equation inside that range was minus h² squared over 2m, second derivative with respect to x of, let's say, psi x. That was just some energy times psi x, right? So you multiply both sides of this equation by f of x. The equation we have is identical. Second derivative with respect to x of f of x is this ex, which is a number, times fx. So we're basically done. We know the solutions to this, and we know the boundary conditions, again, work, right? So here we want the wave function to vanish if, for example, x is 0 or x is equal to L, and that's the case because if we take the solutions of the one-dimensional problem, f of x will vanish if x is equal to 0 or x equal L. So then it kills the product will be 0. So if each of these terms is 0, the product will be 0. So we're done. We can just recycle the solution to the 1D problem and say, well, f of x is going to be some number times sine of an integer pi x over L. Fy is going to be some number times sine of another integer. They don't have to be the same necessarily, pi y over L. And this is gy we called it. And hz, again, it's the same structure. So we use the cube, right? We assume the dimensions are the same. Could easily just make it like a make it like a rectangular box where we have different Lx, Ly, and Lz. But let's just stick with the cube. It doesn't really change anything. All of the steps will go through if, these lengths on different directions are not equal. And then, again, we know the energy for each of these, right? We know that those energies are proportional to nx squared and y squared and z squared. So you add them up, we find that E of now nx and y and z. So basically our wave functions are labeled by 3 integers instead of 1 integer, right? They're the product of these things. Ax, Ay, and Az are just some normalization constant. We can combine them and normalize at the end. Or, you can just pick the normalized one. So you can use Ax equal Ay equal Az, whatever normalized the 1D problem, because the three-dimensional integral factorizes into 3 one-dimensional integrals for normalization. And if each of them is 1, the product is 1. So this is something that works. That normalizes that entire wave function, which is the product fgh. And of course, this energy takes the structure. Let me write the result here. Going to be pi squared h bar squared over 2m 1 over L squared. and I have nx squared plus ny squared plus nz squared. So that's just reading off the solution of the one-dimensional problem for each of these terms. Okay, so that's a simple problem in 3 dimensions where we exactly managed to find all the energies and all the wave functions that solve the time-independent Schrödinger equation with this potential. So one interesting observation is that previously when we classified, let's say, all solutions of a one-dimensional problem, like particle in a box in 1 dimension or the simple harmonic oscillator in 1 dimension, we managed to label our wave functions and the associated energies with just one integer. Here it's much more convenient to label them with 3 integers corresponding to these three different dimensions in this case. But yeah, as we will see, the same type of structure appears even if we go to like a different coordinate system. So the next topic I want to talk about is the hydrogen atom, and again so I'm going to write the Schrödinger equation, and we won't really solve the hydrogen atom. We don't solve that differential equation. It's a little bit beyond the level of this course, but I'll give you the solution, and again it's going to be a solution labeled by 3 integers. They have kind of different interpretation than in this case, but that's a very useful way of thinking about the hydrogen atom. So if I want to, let's say, think about the hydrogen atom, it's the simplest atom, and the assumption is that the nucleus is kind of heavy, so it doesn't move much, so basically the center of mass is pretty much the same as where the nucleus is. So you have some proton here, and then there's an electron that somehow interacts with this proton, is bound to the proton. They attract, right? This has positive charge, this has negative charge. So the way to think about it is to again see what is the total energy. And if we forget about the kinetic energy of the proton, assume it's much heavier and it's not moving much if we go to the center of mass frame. So basically the center of mass is, by assumption, yeah, we neglect the difference between the center of mass of the system and the center of the proton. So all of the kinetic energy comes from the motion of the electron. So let's say electron mass is m. So I can write my kinetic energy operator is going to be minus h bar squared over 2m. If you write your Schrödinger equation in Cartesian coordinates, we just found the kinetic energy operator. That's it. Now, what is the potential? Well, the potential energy is going to be the Coulomb potential energy between 2 charged particles. So if you have 2 charged particles, the potential energy, let's say this distance is r between the two, then the potential energy, let's call it, so this is kinetic energy. It just depends, as you remember from your electromagnetism courses, it just depends on the distance between the 2 charged particles, and it's in SI units, it's I think minus 1 over 4 pi epsilon naught E squared, where E is the charge, over R, the distance. Okay, so if you want to write it in Cartesian coordinates, you would right, u of x, y, and z, right? For any point in three-dimensional space, u is this. So it just happens to depend on a particular combination of x, y, and z, which you can write as the square root of x squared plus y squared plus z squared. So it turns out to solve the Schrödinger equation in Cartesian coordinates, that's really a nightmare, because we're not making use of the fact that this potential depends only on one thing, only depends on the total distance, right? So this is a much simpler form than that. So basically we're saying if you have x, y, and z, your potential only depends on the distance between the origins. So I've put my proton at the origin and the electron is somewhere in this coordinate system, has components x, y, and z. The electron is somewhere, so it only depends on this distance. And there's an alternative way of representing position. They're known as the spherical coordinates, where you represent the position with a distance and two angles. And it turns out that this change of variable is extremely useful in solving problems where you have a potential that only depends on distance and doesn't depend on the angle. So basically, in general, imagine imagine this vector makes an angle theta with the z-axis. So theta can be between, let's say, 0 and pi. So it's somewhere, 0 is all the way here, or it goes all the way down to minus c. And then once you project the position on the xy plane, this projection makes an angle phi with the x-axis. So phi can be anywhere, right? If you look at it from the top, can be anywhere on this plane. So it goes between 0 and 2 pi. And then you have r, which is not negative. It's a non-negative number, which is really the length of this vector. So kind of we have Cartesian, where you have x, y, and z. You specify x, y, and z. You know where that point is in three-dimensional space. Similarly, you can use spherical coordinates, and you specify r, theta, and phi. And if I give you these three numbers, again, you know exactly where that point is in space, right? So if I specify r, that gives you the surface of a sphere, like that's the set of all points that are a distance r from the origin. And then if I give you the angle theta, right? So first you have the sphere here of radius r. The angle theta, the points on the sphere that form an angle theta, you can just pick one point and rotate it around, so it's going to be some circle. And then the angle phi picks one point on this circle. So specifying these three numbers is enough to know where the point is, in the same way that specifying those three numbers, x, y, and z, was enough to know where my point is. And these things are mathematically related, right? So we already said that r is, for example, square root of x squared plus y squared plus z squared, right? So if this length here is x, this is y, this length of the projection is the square root of x squared plus y squared, and then here you have if I look at this triangle, here I have square root of x squared plus y squared. Here I have z going up. So then r becomes square root of this thing squared, which is x squared plus y squared, plus this thing squared, which is z squared. So it's going to be that. All right. So let's also go the other way. So I can go, for example, from spherical to Cartesian, right, to relate these a bit more. So you can say, well, if this angle is theta and this is r, what is this length here on the xy plane? It's going to be r times sine theta, right? So then the x becomes r times sine theta times cosine phi. Cosine, this is adjacent, so x is r sine theta cosine phi, y becomes r sine theta sine phi, as you can imagine, and z is simply r cosine theta, right? You project here, you have a right triangle, z component is adjacent to this angle theta. So that's a recipe for our change of variables. There's also kind of an inversion of this, so you can, again, I wrote r theta becomes inverse cosine of z over that, over r. Just from this equation, cosine theta is z over r. And phi becomes inverse tangent of y over x. Again, you look at y over x, r sine theta goes away, so tangent of phi becomes y over x. All right. So it turns out this is a much more useful representation, because now this potential doesn't depend on two of the coordinates, right? So that should allow us to simplify the equation quite a bit. All right, so let's keep going with this. So in order to write our equation completely in terms of r, theta, and phi, of course, we need to write this operator in terms of r, theta, and phi. And it's an exercise in calculus using kind of playing with partial derivatives, etc. So I won't go through the details of that derivation, but you can imagine, like, it's a change of variable, right? So when you're taking the derivative of a function with respect to x, x is written in terms of r, theta, and phi, and kind of taking derivatives with respect to r, theta, and phi should have the same effect with some coefficients. So basically, this operator is called the Laplacian, after the French mathematician Laplace. That's the notation, like an inverted triangle squared. So in Cartesian coordinate, that's the operator. Second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. And we can write the same operator, so something that has the same action on some function of all coordinates upon this change of variable, in terms of the spherical coordinates. So it turns out this operator is written as 1 over r squared, derivative with respect to r squared, derivative with respect to r. So again, the interpretation is when it acts on some function of, let's say, r, theta, and phi, first we take the derivative with respect to r of that function, we multiply the result by r squared, and then we take the derivative of the whole thing with respect to r, of this product with respect to r. Then we have 1 over sine theta, derivative with respect to theta of sine theta, derivative with respect to theta. And then we have 1 over sine squared theta, derivative squared, second derivative with respect to phi. So that's basically the same operation in terms of these coordinates. Okay, so to write the Schrödinger equation in terms of these spherical coordinates, we would write minus h bar squared to m. This Laplacian operator, which has this form in terms of r theta phi and the derivatives with respect to these coordinates, then plus u of r, which in this case is minus 1 over 4 pi epsilon naught e squared over r. So this again is inserted in this form, times some function of r, theta, and phi. This should become some energy times the wave function. All right, so think of it as a change of variables. Now we have to talk about two things. So one is how do we interpret this? Like, what is the notion of probabilities? So we have to think about the volume element in spherical coordinates. And then the question is, like, what are the integers this energy depends on, right? Remember, in this one example where we solved it, we had 3 integers which parameterize the energy eigenvalue. So in this case, for the hydrogen atom, this problem here, again, there are 3 integers. Let's call them n, l, and n. So 3 quantum numbers. So I will talk a little bit more about what these are and what the energies are, what the wave functions are. Similarly, the wave functions are labeled by these integers. Okay, so we want to talk about 2 things, right? One is elaborating more on these wave functions and the associated energies. Another thing is just talking about interpretation of probabilities. So in Cartesian coordinates, we said if we look at some point and let the coordinates, namely x, y, and z, change by some infinitesimal amount dx, dy, dz, we form a cube, we form a volume element whose volume in 3 dimensions is just simply the product dx, dy, dz. Now, if I go to spherical coordinates and look at some point, okay, so now let me allow, from this point, let me allow r to change by some amount dr, right? I allow theta to change by some amount d theta. So if this is theta, we just add some d theta to it, right? D theta here. Already you can see that in terms of the actual length, this length here, that's perpendicular in the limit of tiny d theta to this dr, let me write it here, has a length r d theta, right? It's a tiny arc in a circle of radius r that has an angle d theta. And we know that the perimeter of a circle is 2 pi r. 2 pi is like 360 degrees for the full circle. And we know the length of the arc is proportional to the angle, so this tiny length is going to be r d theta. So now we have this kind of this element like that of area, this 2-dimensional surface area, r d theta, And now this thing rotates around the z-axis, right, by some angle d phi. As you add a little bit to phi, this whole thing kind of rotates around this, and there's going to be an additional, so that's going to be the height over the surface area, which would give us the volume. So something like this. Right, and then this little thing, okay, so what is that? Well, again, that's when you look at it from the top. What do we see? We see that as you rotate, you know, here this length is r sine theta, right? This is r from here to here. This is theta. This is opposite the angle theta in a right triangle. So looking at it from the top, we see a circular radius r sine theta, and then this angle here is d phi. So this third length here is going to be again r sine theta d phi. So now that the volume of this element dv, as you change r, theta, and phi by some infinitesimal amounts, the volume you create, the volume you cover, is going to be the product of these three things, right? So it's going to be, it's not just dr, d theta, d phi, it's going to be r times r is r squared, and then we have a factor sine theta from here, and then we have dr, d phi, d theta. Okay, so then the interpretation of the wave function is that the probability of measuring position in volume dv, this volume here, which is located at r, theta, and phi, and has, you know, infinitesimal variations dr, d theta, d phi, is going to be psi of r, theta, and phi absolute value squared, the wave function, times the volume element. So times r squared d theta dr d phi. So now the normalization condition becomes what? Normalization is that sum over all these probabilities is 1. So it's going to be 1 is equal to integral r goes from 0 to infinity. Theta goes from 0 to pi. Again, going back to this picture, theta goes from here all the way down, and phi goes from 0 to 2 pi. Of psi r theta phi absolute value squared. Oops, I have a sine theta here, right? That's also part of the volume element. So r squared sine theta. So that's my normalization condition. If you have like a wave function in Cartesian coordinates, it's kind of simpler, right? Normalization would be, if you have your wave function in terms of x and y, then it's all of them go from minus infinity to infinity. The element of the volume, you also have d phi here, is dx, dy, dz. Right, this is just the volume element here. This is the volume element. And then we have the wave function, absolute value squared. Okay. Now, if I want to find, let's say, some expectation value of anything, you want to find, for example, the expectation value of r what is it going to be? Well, the expectation value of r, the distance, for example, that's the probability. For that probability, r is fixed, so it becomes, you just insert the thing you want to find its expectation value inside the integral. So it's going to be r psi r theta phi absolute value squared, r squared sine theta d theta dr. Have to be careful about the order here. So the inner one should be phi, that goes from 0 to 2 pi, right? Then theta goes from 0 to pi, and r is last. Similarly, let's do it here. d phi, d theta, dr. Okay. So that's a general discussion about like treating wave functions, probabilities, expectation values in spherical coordinates. Now let's focus on the particular case of the hydrogen atom. So for the hydrogen atom, as I mentioned, there's going to be 3 integers which determine our wave functions, and the energy just depends on one of them. So we have En Ln is just En. It doesn't depend on L and M. It doesn't depend on those 2 other integers. The wave functions do, but the energies don't. And it turns out that the answer here in electron volts is minus 13.6 eV over n squared. And n can take the values of 1, 2, 3, 4, up to infinity. Okay, so those are the energies. Now for each of these, we can have a value of L which runs from 0 to n minus 1. And then for each L we have this. So this is known as the principal quantum number. This is known as the total angular momentum quantum number. So of course there's an interpretation related to angular momentum which we're not discussing in this course, but this is physically related to the total angular momentum of this electron that's going around the nucleus. Qn for quantum number. And then there's a last quantum number m which runs from minus L to L. So minus L plus 1 changes by increments of 1 and goes all the way to plus L. So this is related to the z component of angular momentum. Okay, so this is a good place to stop. So next time we'll continue this discussion. I'll show you some visualization of the wave functions. We talk a little bit about the wave functions, the transitions that occur as electrons, for example, get excited to higher energy level and then kind of decay to a lower energy level. They can emit a photon, and the energy of that photon is the difference between these energies. So basically like a transition between 2 levels with a certain principal quantum numbers gives you the energy of the photon that gets emitted. As you can see, there are a certain number of states corresponding to each energy, so we talk a little bit about that. So yeah, so next time we'll continue this discussion of the hydrogen atom.